Good afternoon, everyone. I'm Gao Qidi from Shanghai Jiao Tong University, the Computational Maritime Hydrodynamics Lab. And I'm going to talk about our work about numerical simulation of JBC shape weak based on well-modeled edge, large eddy simulation. And I will introduce in these 5 parts. First, I will give a brief introduction of what we do. We are investigating the shape weak flow. As we know, the shape weak can influence the navigation, attitude, and handling of the ship. So it has a significant meaning to investigate this complicated flow field. And how we research the weak flow. It has 2 ways. The first is experiment. We can use facilities to measure the flow field like beetle rake. And nowadays we can use PIV systems get the refinement flow field of the ship wake by towing tank or circulating water tank. But about model experiment, it has its defect like high cost, low repeatability, and low universalities. So if we want to have a model experiment, we need a long period to get what we want result. So we have another way to investigate the ship flow is numerical simulation. It has no defect like model experiment, but it has itself disadvantage is the accuracy of the numerical method. So in our work, we want to find a good way to have a good simulation of shape weak flow. And next, I will introduce the target we used to simulate about simulation. It's Japan Bunk Carrier, which we called JBC. The JBC is a capsized bunk carrier equipped with a stern duct as an energy-saving device. And the principal particulars of the shape model is like this table. The length of the model is 7 meters, and the draft is 0.4125. In the model experiment, the results of stern flow field are from towing tank experiments which were performed at National Maritime Research Institute, which we called NMRI. And it has 3 slides of ship wake. It's S2, S4, and S7. Oh, this it's the version of the PowerPoint. And in right figures, it shows the experimental results of each slice of the ship flow. And we used this as a basic to compare with our result. Before our simulation, it has many organizations and institutions provide numerical simulation results of JBC wakes. The turbulence model they used is almost K omega SST model or K omega or K epsilon model. And in right figures, it shows one result of S2 slide used K omega SST model. From the result, we can see it is inaccurate about velocity distribution, flow field, and turbulence structure. Especially the near wall region, we can see the detailed vertex structure cannot found in the simulation result. So in our work, we want to find a good way to have a refinement result to get a detailed turbulent structure, use wall-modeled LES method. And then I'll introduce the wall-modeled large eddy simulation. It has two ways about this method. One is hybrid LES and the RANS model, which we call the detached eddy simulation (DES). In this way, the calculation region is divided in two parts. One is near wall region, what we call the inner layer. We use RANS model to solve this region. And in outer layer, we use LES method. And about wall stress models, we call the wall model the large eddy simulation. In near wall region, we use model the method to this model method is to create a wall model to solve the inner region, and in outer layer we use large eddy simulation. In our work, the Openfoam platform is V10. And next, I will introduce the numerical method of wall model the large eddy simulation. This method is open source library called the Libo model the LES produced on Macau. And the unstudied filter NS equations for incompressible flows is as shown. In this equation, it has a tau SGS parameters, and it calculated by this right equation. In this formula, it has a VSGS. What is the eddy viscosity computed by the SGS model? And the VSGS is given by this equation. In this equation, the CW is it's a empirical parameter, and the SIJ is the resolved string rate tensor, and the SD is the traceless symmetric part of the squirrel of velocity gradient tensor. The wall stress model is given by the thin boundary layer equation like this, and the solver we used is Openfoam, and the Gauss linear difference is we used to. And then I will introduce the computational setup. And the model we choose is the model experiment GBC model. The length is 7 meters and the draft is 0.4125, and the free surface is not considered. The computational domain is 4 times LPP in length, and 1 in depth and 1 in width. The flow velocity is 1.1779 meters, and it's the same with the model experiment. The upper surface of the computational domain consists with the water line of the GBC shape. And that is the mesh of the computation. The mesh are generated by SnappyX mesh in Openfoam. Because we want to have a detailed flow field, so the mesh is the important part of our research. We create refinement grid in near wall region, and you can see in high detail and the middle part of the shape. We add the 12th layer in the turbulent area, and in right is the tail of the GBC Oh, in the machine, we found we have a lot of tests. At the beginning, we set background grid is 70 and 20 and 20. We want a cube grid to. We think it can be have a good quality of the mesh, but like you see, when the background grid is this set, the refinement mesh is not good enough. So we have a lot of try to have a good mesh in the near wall region. After many tests, we found another background mesh to have a refinement grid in near wall region, like 27 and 20 and 20. We totally make 3 set of grid, 10 million, 20 million, and 40 million. In each grid, the thickness of the first layer is as shown in table. Because the LES method is sensitive about Y+, so we are the background grid is shown in the middle. In the simulation, we set a comparison. We use WRLES and RANS and DS to compare with the wall model method, and each of them used the 10 million grid to have simulation, and delta T is 1,000. The first we calculation 20 seconds, and in order to compare with the experimental results, the flow field is averaged by last 5 seconds. The resistance is measured, and in the model experiment, the total resistance is 75.1 Newton. And then I'll introduce the result of our simulation. First is the resistance. In the left figure, it is 4 methods of the resistance. First, I'll introduce the WRLES. You can see the resistance of WRLES is far away from the right resistance. And why this happened? Because the WRLES method needs a very critical Y+. The Y+ should be less than 1, but Y+ value in our mesh is bigger than 42. So in WRLES, the mesh cannot sufficient to have a accurate result. So and about RANS method and the DS method, the resistance is close to the experiment result. But the WMLES is smaller than the result, and I'll explain why this happened later. And another we found with WMLES method is oscillation simulation of numerical oscillation. You can see it has a very big resistance in the total 3 seconds. It's a non-physical phenomenon. In our actual work, we found this situation, and we can't explain why this happened. We think it's a basic wall model about how they solve the equation. And then it's the flow field of it's a weak flow. You can see the in 10 million grid, the WMLES has a in velocity distribution, it's generally the same, but the speed of the velocity is bigger than the experiment result. And in 40 million grid, the accuracy cannot be better, and I will explain why this happened. Compared with DS and the RES method, we can see in the DS method, the result is the best and the RES is the worst. Compared with the other two methods, the result after time averaging are still not stable. The velocity near the wall is about 10% higher than the experimental result. The turbulence structure near the wall is not fine enough. And that is the conclusion. The WMLES method is very sensitive to the number of the grids and especially Y+. And increasing the number of grids and reducing the value of Y+ will not significantly improve the simulation results. And the simulation accuracy of the near-wall turbulence structure is low, and the calculated flow velocity is larger than the experiment. In the future work, the influence of Y+ on the accuracy of WMLES calculation, the Y+ should be between 50 and 150. That's why the grade of the number of grade increase has not accurate result. The Y+ in WMLES should be bigger. It's not same with the WRLES. And investigating the influence of different sampling heights H on the accuracy of calculation result in explored. In future work, we will continue the WM method and find a new method to simulate shape weak flow, and using different shape model to verify the characteristics of weak field calculation, and investigate the calculation method of the real scale shape weaks. And that's my presentation. Thank you.
Thank you. Questions, please? Okay, may I start?
Oh.
Okay, so first I can fix your fluctuations in the force. Okay, so if you put the slide on where you specify the settings for discretization.
Yes, so.
Okay, if it's a problem, don't worry about it. I can just help you.
Oh, wait a minute. Sorry. Oh, okay.
When you specify the settings for discretization, your Laplacian scheme says Gauss linear corrected.
Yes.
Non-orthogonality in the mesh is probably bigger than 80 degrees.
Oh.
You cannot use a corrected scheme. It needs to say Gauss linear limited 0.5.
Oh.
And you also need to use cell limited on the gradient scheme.
Oh, okay.
So that will remove your fluctuations in the force.
Oh.
The second thing is, unless there are questions, I'll carry on. So please interrupt me. The second thing is that this is still a model scale ship. It's about 7 meters long.
Yes.
And your Reynolds number is not very big.
It's 7 million. 7 and 26 million.
Okay. On a full-size ship, it will be 10 billion. Okay. You have no business running large Eddy simulation for this ship in order to get ship resistance. Okay. We did lots of experiments with that, and you have to have two conditions. First one is Y+ needs to be 1 or less.
Oh, yes.
Not 5, not 10.
Yes.
1 or less.
Yes.
And the second thing is you will want your code to resolve what is going on next to the hull. And for that, you need to have IDDAS schemes, which will protect the near wall region to operate in the RANS regime.
Yes.
Okay. This is very hard because there is no general criterion in IDDS to recognize the near wall layer.
Yes.
And if you switch from DES to inappropriate treatment, you're going to get the force which is about 20 to 30% too low.
Yes.
Okay? I have one more concern. Even your run simulation is not accurate enough. Okay? So you said that the measured ship resistance is 35.1. Okay? For normal circumstances, even when you take into account the free surface, the acceptable error is about 1%.
Oh, okay. Yes.
So you can have 34 or 36, but in fact you have 30 or 28. Okay. So my advice is, if you're looking to calculate the ship resistance, you need to use wall functions and runs. When you're doing LES with ships, the meshes are going to be much larger.
Yes.
Okay? So the ones that I have done are 160 million cells with adaptive mesh refinement. And the only reason to run them is to get off-body vortices.
Yes.
In that case, I know that my ship resistance will be wrong, but the off-body vortices and the weight will be good.
Oh, yeah. Yes.
Okay.
Yes.
So please consider that, because comparing ship resistance with LES is something that we are going to do in 10 years' time, because today